Now, if we now go back and look at the rotations between the fields phi1 and phi2. So we all started with a real scalar field, and we said, okay, let's have two. And then we said that, okay, let's assume that these two real scalar fields have such and such a symmetry properties, like the ones appearing over here. And then instead of working with phi1 and phi2 separately, we define their linear combinations. So how will those fields change under this rotation?
Can I add something to this?
Please.
What we are doing actually is to take the space in which these fields are flat, are homogeneous, or at least homogeneous. What we can do is actually, in general, and these are called nonlinear signal models, is to define a metric on the space in which these fields live.
Okay. Now, there are lots of things you can play around with, but let's stick with the basics for the time being. So let me look at phi. Phi was 1 over 2, phi1 plus I phi 2, under 1 over square root of 2. Under these rotation, this will become 1 over square root of 2. Okay, phi 1 is cosine theta phi 1 plus sine theta phi 2 plus I phi 2 will be minus sine theta phi 1 plus cosine theta phi 2. Now, I would like to somehow simplify this. Let me say this is 1 over square root of 2. The terms proportional to cosine theta will be phi 1 plus I phi 2. And the terms proportional to minus I sine theta will be phi 1 I phi 2. Now, when I look at these transformation properties of phi 1 plus I phi 2, when I transform it, I obtain something that depends only on phi 1 plus phi 2. Well, this is equal to c theta.
I think we've made a sign mistake.
Why?
It should be minus I phi 2.
Why?
What is it?
You see, this is plus sine theta phi 2.
Correct, that's correct. Phi that.
Well, let's see, this is c theta cosine theta minus I sine theta phi. But that is nothing but e to power minus I theta phi. So phi goes to e to power minus I theta phi. This is my symmetry now. Well, it's not a big surprise because my Lagrangian depends only on phi star phi now, or the derivatives. But this doesn't change under a phase change in the definition of the field. So I started with real scalar fields that the Lagrangian didn't change under rotation, but those rotations basically correspond to phase transformations for the complex fields. Now the rotations, initially I had this symmetry O2. These are just two-dimensional rotations. Now I have what is called U1. Yeah, multiplication by phi by a phase is just a U1 symmetry. Yes?
It should be SO2. It should be SO2, not O2.
Yes. SO2 because I don't have parity.
Sorry, I missed that. How did we, what kind of transformation made us able to write 5 times a to the minus I theta? Last time I checked, we were rotating each vector field individually.
No, I don't. Look, what I did was I had these real scalar fields, not even vector fields. I rotated them to each other. I have this rotation between them. So I wrote a theory which was invariant under rotating in this hypothetical two-dimensional real scalar space. But then I defined a complex field using my real fields. And for this complex field, the symmetry of rotating these two real fields into each other is actually just multiplication of this complex field by a phase. They are the same thing, basically. By the way, my symmetry, initial symmetry, is O2, not SO2.
Even if I add to parity, but
Yeah, my Lagrangian is invariant also under parity.
but would it give me the orthogon over this still high, even if I add the discrete transformation?
O2 is parity plus rotations. My initial Lagrangian has this O2 symmetry.
But the symmetry you have is
The symmetry we have now is U1, which came from the SO2 part, and parity is still there.
but the transformation that you do is cosine theta minus sine
Yeah,
theta.
that is SO2. Yeah. My initial theory still had O2 symmetry, not SO2 symmetry.
But the transformation determinant is 1.
Sure. Let me repeat myself. The initial Lagrangian I wrote had an O2 symmetry because it was also invariant under phi 1, phi 2 goes to phi 1 minus phi 2. My Lagrangian is also invariant under this one. So it's invariant under rotations, that is one thing. Rotations is what we call the SO2. And rotations corresponds to U1. So these two correspond to each other. Now my initial theory also had this parity symmetry, this one. My final theory also has the same parity symmetry, which corresponds to phi, goes to phi star. But what corresponds to U1 is SU2. I agree with you on that. But I also have this parity thing aside.
But that parity already is a special case of U1 transformation.
No, it shouldn't. No, it's not. You see, parity in the complex field case is complex conjugation, not multiplication by minus sign. You see, this is my parity transformation in the complex field case. And in fact, it's C parity, to be more precise. Because if I take, if I replace phi by phi star, basically these two A and B's, they are being exchanged. A and B are particles, are particle and antiparticle. They will be antiparticles. We will come to that later on. So for the time being, let's just keep in mind that another field I can define is the complex fields, and in this particular case, I have a complex field with this U1 symmetry. Now I'm emphasizing this symmetry because I will be using this symmetry probably in the next hour. We will start looking at the Noether theorem. But before that, let's look at the vector fields. So we in fact already had seen an example of a vector field. If you start with this one, the three-dimensional lattice, take the continuum limit, you have to talk about some vector fields. Vector fields corresponding to the displacement in x, y, and z direction. So basically this del mu phi, so we had such a term. Well, we have two problems though. I might be tempted to replace this with del mu I. Well, I have the x, y, z directions, but I should have 4 components. So I should also introduce the 0th component, del mu A nu squared.
Now we change the vector field, right?
Yeah, now it became a vector field. Okay, the more well-known vector field we will have is the vector potential in electromagnetism. This A mu, you have the scalar potential and the vector potential. We have the Lorentz field strength tensor. And we usually write the Lagrangian as minus 1 over 4 squared. Well, what do we have here? We have the 1 over 4. If I take the square here, del mu A nu squared. Then I have plus del nu A mu squared. And then I have minus twice del mu A nu del mu A mu. Well, these two terms are identical. Do you see that? Because nu and mu are dummy indices. In the square, they appear twice. I can just change their names. So if I, in the second term, if I change the name nu to mu, and if I change mu to nu, then the second term just becomes the first term. Well, the first term is what we expected, if you like. The second term is kind of extra. But again, it's the derivative term, so it will be also it will give us the dynamics of the system. In fact, if you just forget that term for the time being, let's just ignore it for the time being. If you just look at this term, it's still weird because you see in the scalar case, we had the plus 1 over 2 del mu phi term. Here it is minus del mu A nu squared. But keep in mind that that is minus 1 over 2 del mu A0 squared plus 1 over 2 del mu AI squared. So again, if you just look at this term, it's still positive. Now, I won't go into too much detail about these theories because we will see them later on, probably in more detail next term rather than this term. Because you see, if you start with, let's say, the oscillations in the electric field, well, you have 3 degrees. If you look at the photon, the vector particle, you have basically 3 degrees of freedom. But now here we have 4 components. Don't we have 4 degrees of freedom? Well, actually, no, we don't. We only have 3 physical degrees of freedom. I mean, it will be a whole month probably to discuss what happens to that extra degrees of freedom, so I will just leave it here. So this is what we have. Let's derive the equations of motion. And before deriving the equations of motion, let me also add another term here, J mu, A mu. J mu is something I invented, some kind of an external field, if you like. So what will be the corresponding equation of motion? Well, our Euler-Lagrange equations is always the same, del mu, del L by del mu A nu, minus del L by del A mu. This should be equal to 0. Del L by del A mu. Well, you see the first term, I only have the derivatives, so it doesn't contribute. This is the only term that contributes. So del L by del A mu will be just J mu. Well, let's look at del L by del mu A nu. Okay, I emphasize mu and nu are dummy indices, not dummy indices. They are not dummy indices in this derivative. They are explicit indices, free indices. But the mu and nu in my Lagrangian are the dummy indices. So this will be equal to minus 1 over 4 del over del A del mu A nu del alpha A beta minus del beta A alpha squared. Now the mu and nu appearing in this Lagrangian, they are the dummy indices. I shouldn't confuse them with my explicit indices, so I just change the name of my dummy indices to some other name. Now this will be minus 1 over 2 del alpha A beta minus del beta A alpha. Derivative with respect to del mu A nu of del alpha A beta minus del beta A alpha squared, no, not squared, no squared. Well, in the first term, alpha and mu should be equal if I am supposed to get some non-zero index, and beta and nu should be equal. In the second one, beta and mu should be equal, and alpha and nu should be equal if I am to get a non-zero value. Again, I repeat, I'm just ignoring the position of the indices. They can be upper index, lower index, but with this, ignoring the position also tells me that G mu nu is equal to, because formally speaking, Kronecker delta has one upper and one lower index. It doesn't have two lower indices. It doesn't have two upper indices. One of the indices should be lower and upper. Formally correct form is this one. But since I'm ignoring the upper and lower indices, I write everything as lower index. Now, if I multiply these terms, what I will get is minus 1 over 2. Okay, this product will give me del mu A nu, and this product will give me minus del nu A mu. These two terms will give me del nu A mu, a second one of these, and this product, if I multiply the second terms in both parentheses, will give me the first one. So I get minus F mu nu. So my equation of motion is del mu minus del mu F mu nu minus J mu is equal to 0, or del mu F mu nu is equal to minus J mu. Okay, let me just change some signs. This is minus, so this becomes minus, this is plus, this is plus. Well, if J mu is the electric current, well, this is nothing but my two of the Maxwell's equation. So I recover the Maxwell's equations starting from this Lagrangian. So any questions up to here? So now finally, let's start with Noether's theorem. you have probably seen some form of this in classical mechanics or analytical mechanics, right? Do you remember? So, for example, if you have a Lagrangian that is translationally invariant, you have a corresponding conserved quantity, which will be the momentum. If you have a Lagrangian that is rotationally invariant, then the conserved quantity will be the angular momentum. From a Lagrangian which has time translation invariance, you have the conservation of energy. If you have a symmetry, you have a conservation. That's the basic idea of the Noether's theorem. If you have a conservation, you have a symmetry. If you have a symmetry, you have a conservation law. Well, the same thing also holds here. If you have a symmetry, we should get a conservation law. Now, we had already seen many symmetries, like for the complex field, we have this symmetry under phase redefinitions. So let us be a bit more concrete by what we mean by the symmetry. The thing that determines the physics of our system is not the Lagrangian itself, but the action. That will be crucial. So let's say that this is the action. Well, the action will depend on my fields. It can also depend on my the derivative, the conjugates of my fields, etc. But let me just write it in this form. It depends on my fields. What I mean by a symmetry will be, I have my field phi. I replace it by some other field, let's say phi prime. I want S of phi to be S of phi prime plus some constant at most. Now that constant, I don't really care about that constant because what will be important for me is the variation of the action. So in principle, I can have some constant. So my Lagrangian will also be a function of phi. What this would mean for my Lagrangian is Lagrangian of phi and Lagrangian of phi prime might differ by a total derivative. In fact, for such a transformation, if your fields go to 0 at infinity, that total derivative will just give you 0. It will be a boundary integral. I mean, the Lagrangian need not be invariant under my transformation, but if it differs by 4 divergence. That is what I will be looking at. If you go back to the cases we considered, for example, well, this will be the first one I will study. Under such a phase redefinition of my fields, this just becomes 0. There's no total derivative that comes from that transformation. But it might happen that under certain symmetries, Lagrangian is not invariant, but the change in the Lagrangian will be a total derivative.
The necessary that we're talking about is the first, right? About global symmetries.
Yeah, for the time being here, I'm not even specifying what I mean by this phi goes to phi prime. Phi prime can be something defined in terms of phi, or whatever you want. It will probably have some parameters also. I'm not specifying anything for the time being. I'm just saying that let's assume that I have my fields phi. I just change their definition somehow. I define new fields phi prime. For example, in the case of global phase transformations, this phi prime will be just e to the power minus I theta phi.
That vector k is defined such a way that it is 0 at the boundaries, right?
I always assume my fields are 0 at infinities, so that the integral of that k over the surface at infinity will be 0.
It doesn't depend what kind of vector or field it is, right? For this assumption.
The only thing I'm assuming is the change in the Lagrangian is a total derivative. I don't know what that total derivative is, but if this is satisfied, that is the assumptions of the theorem. I'm making a change in the fields. That's my symmetry transformation. Under this change, the Lagrangian changes by at most a total derivative, if these conditions are satisfied. Then what can we conclude from this? If these are satisfied. Not all Lagrangians satisfy this property under all transformations. Then we say that they are not a symmetry of our nature. Well, what will be the variation of my Lagrangian? You see, phi goes to phi prime, which I'm assuming that I'm making a very small transformation, a very small change. In this case, for example, if theta is very small, this will be phi minus I theta phi. Then phi prime will be just phi plus some very small change in phi. The change in my Lagrangian will be derivative of the Lagrangian with respect to phi times the change in phi plus derivative of my Lagrangian with respect to del mu phi times the variation in del mu phi which will be equal to del mu k mu. Yes, here k mu also depends on del phi, the change in your field phi.
Hocam bir eksi işareti gelmeyecek mi hocam?
Well, del L is L phi. Okay, let me put the minus sign over here. Well, this will be equal to derivative of Lagrangian with respect to phi, del phi, plus the total derivative of delta phi minus del mu del L by del mu phi delta phi, which should be equal to divergence of k mu. But this is equal to delta phi I just combine the first and the third terms plus del mu of del L by del mu phi delta phi, but this is 0 by equations of motion. And what I end up having is del mu del L by del mu phi delta phi should be equal to del mu k mu, or del mu this is equal to 0. Now, IP k mu will also have, depend on delta phi, you might have many parameters, you might have more than one of these equations in your equation, depending on your parameters. But in general, let's say that, let me define this whole thing as J mu. It just corresponds to a conserved quantity. Now, what do I mean by conserved? I can define the corresponding charge. The here charge is named in the general sense. It doesn't have to be electric charge. It's some kind of a charge, which is defined as the integral of the zeroth component. If I look at the time derivative of this charge, how does this total charge changes with time? This is del J0 by del T. It's a partial derivative inside. But this is nothing but gradient of j, L minus the gradient of j, the remaining components, because of del mu j mu is equal to 0. Because of that, I'm basically using that del mu j mu is equal to 0 equation to write this equality. But this is nothing but the integral over the whole surface. Now, you can either say that, okay, my surface is at infinity, then Q is the total charge in the universe, so that surface integral at infinity is 0, and hence the total charge in the universe is conserved. That's one way of interpreting this equation. Or you can say that, okay, I'm not looking at the whole universe, let me just look at a finite region in space. Then this equation tells me that if the total charge within this volume is changing, it is because some charge is either moving out of this region or into the region through the surface. But both imply that the charge is conserved. So this is why we call this equation the conservation. If you get such an equation, you know that there is a conserved quantity there.
For finite volume, how can I tell the total charge conserved?
Yeah, you see, what this equation tells me in some finite region. Now, this equation already tells me that if the charge in this volume is decreasing, it is not because new charge is appearing within this volume or disappearing within this volume. It is because charge within this volume is moving through this surface, either out or in, depending on the side. That is already, in a sense, that's the definition of conservation.
Continuity.
Yeah, this is the continuity equation. This is in a sense, if you like, the expression of charge conservation. You see, this would be, continuity equation is, in a sense, more general,
Right.
let's say, than the conservation, saying that the total charge is conserved in the universe. Because saying that the total charge in the universe would be conserved if, let's say, some charge disappears here and appears at this place. That would still be a conserved charge. The total charge in the universe didn't change. But this tells me that no, that cannot happen. If the charge within this volume is reduced, that can only be if the charge moves from within this volume to out of this volume through the surface. That is the only way that the charge within my volume, finite volume, will be reduced.
So continuity implies conservation.
Yes.
Or it's just one. Yeah.
Yes.
But his question was that the infinite sphere. How do we look if this is for finite radius, right? But your question was.
Yeah. How can I? Yeah, I mean,
we
the idea for infinite case. Well, there cannot be any surface currents on the surface by me taking the integral to infinity. But
yeah, the current is
by
0.
finite, it's not the case.
Okay.
What is the symmetry
Here.
There is a symmetry, there is a conversion.
Now, I didn't mention the symmetry yet. What I said that if there is such a case that you define some new fields by changing your initial fields, and I'm assuming that you can change your fields by very small amounts. That already tells me that you are making a continuous change. So this will be my delta phi. If after you change your fields in some way, your Lagrangian changes at most by a total derivative. If this thing happens at all, then there's a conserved curve. Now the next question is, does this thing happen? Well, we had already seen some cases. Like we looked at this case. If I multiply a complex field by a phase in my Lagrangian that I chose, in this Lagrangian, if I multiply my field by a phase, my Lagrangian doesn't change. It doesn't even get this additional total derivative. So this Lagrangian has that symmetry, and that symmetry should tell me that there should be something conserved that doesn't change as the system evolves. Yeah, that will be basically the electric charge, if these are charged objects. Or we had seen other symmetries like here, this Lagrangian shouldn't change under rotations. It also doesn't change under translations. I don't even restrict, should read. It doesn't change under rotations, it doesn't change under boosts. So it has a Lorentz symmetry. And it doesn't change under translations. Not only Lorentz symmetry, it has Poincare symmetry, including the translations. So it has those symmetries, so there should be corresponding conserved quantities, which will be the momentum and the energy of the system, and angular momentum of the system. But this Noether's theorem is quite general. It says that if there is a transformation which changes your Lagrangian by at most a total derivative, if it exists, then there is a symmetry. There is a conserved quantity.
How can I get, if I take the variation of the L that I define with the, phi prime, I add the conserved charge there, del mu k mu.
That's not the conserved charge. Del mu k mu is not the conserved charge. K mu appears in the definition of the charge, if it is there.
But when I take the variation, how am I getting the, this equals 0 and
Okay. Let me write it more explicitly. What I mean by delta L is L of phi prime minus L of phi. This is what I mean by delta L. So I'm not taking this equation and looking at the variation of that equation. That's not what I'm doing here. I'm just changing my fields, so I'm obtaining L of phi prime, and then subtracting the original Lagrangian from that, what I obtained. And that difference has to be equal to del mu of k mu. If k mu can be 0 also. For example, in this phase change, k mu is 0. Under rotations, k mu is 0. Any last minute questions?
Is it always the case that when the action changes by a constant, the Lagrangian changes by the divergence of the core vector, or is it specific?
Well, constant basically means you can evaluate that integral explicitly. I would expect it to be so, yeah.
Regardless of number of fixed endpoints, we assume fields that there's no variation at the endpoints, right, to do this. But if you have
this is the thing I use. If it is the total derivative, if I'm calculating the action by integral over the whole space, then this condition tells me that the action doesn't change if the fields are 0 at infinities. But you can have the fields have constant non-zero values at infinities. In that case, I might get some constant value. Constant in the sense that the values of the fields at infinity is constant. Okay, so next Monday we'll keep having lectures. We will have 4 hours of lectures next Monday, and the following one we will have the question solving hour.
that's going to be on Mondays?
On Mondays, yes.